Okay, so we left off talking about mixtures, homogeneous mixtures. Remember, the biggest difference between the two types of mixtures, homogeneous, uniform, heterogeneous, not uniform. Heterogeneous has many different phases, it's called, or parts. Homogeneous, one phase or one part, okay? Even though there's more than one thing in here, we say it has one part, one phase, because it looks like it does, all right? We can separate heterogeneous with filtration. We separate homogeneous with boiling points, evaporating, or distillation. Last thing I want to do with that, so more about distillation, is I don't think I had you draw it. I'm going to have you draw it this time. Let's say we have a container. Let's draw a box or whatever. In the container we have three gases, O2 gas, N2 gas, and carbon dioxide, CO2 gas. So we have three gases, okay? Three gases. Actually, you know what? Let's do two boxes. One box with gases, one box with liquids, okay? So in the bottom here, let's say we have water, H2O liquid. Let's say we have ammonia, NH3, liquid, which doesn't make a whole lot of sense, but that's okay, we should write it. NH3 liquid, and I don't know, let's go with carbon tetrachloride, CCl4 liquid. So we have three liquids in that box on the right, three gases on the box on the left, in the box on the left. In order to separate, we want to separate both boxes. In other words, isolate each gas, isolate each liquid. This box over here, we could use distillation. Use distillation to boil the liquids one at a time. Oops. One at a time. Because all three liquids, water, ammonia, and CCl4, will have different boiling points. They'll have different boiling points. We know water, I'm just going to make these up off the top of my head. Water boils at 100 degrees Celsius. Ammonia boils, I really actually don't know, let me just say 90 degrees Celsius. CCl4, let's say, boils at 70 degrees Celsius. So if we know those three liquids boil at three different temperatures, if we add heat, okay, we put some heat on the bottom of this, you don't have to draw that, but if we heat this container up, whether it's a beaker or a flat or whatever it is, okay, we heat it up and we have some sort of valve at the top, okay, that we can regulate, open and close. Which one's going to boil first and exit the box? Which one's going to boil first? Laura. CCl4 is going to boil first, okay? So this one's going to go out. Let me seal it. Now we only have water and ammonia. Who's going to boil next? Laura. The ammonia is going to boil next. And then water would be boiled last, or we could just leave the water in there. In other words, once those two boil and evaporate and we can collect them, water will be separate, right? So if you want to separate liquids, use boiling points. What would we use to separate three gases? They're already boiled, right? They're already above their boiling points while they're gas. How would we separate three gases? I put a container on the table here. There's three gases. I said your final exam is to separate them successfully. What would you do? We didn't really clarify. Use distillation to separate liquids. If you go back and actually look at your notes, you're going to be like, what? So we're using distillation. I didn't actually write it. We want to separate them. Sorry. How do we separate the gases? Come on, think. I'll give you a huge hint. You can't heat it. Earl.
Chill it.
Chill it. Just chilling. To separate gases, you can, I'm not going to write chill it, decrease the temperature, but that's correct, until each one condenses or if you keep making it colder and colder, what will happen? They freeze or freezes. So if we were to look up, you know what? I'll do it real quick. I'll use the internet here real fast. If we look up the boiling or the freezing point, or no, we'll do boiling points. So boiling point of, what do I have in there? Oxygen. Boiling point of oxygen is negative 183 Celsius. Negative 183 degrees Celsius. That's the boiling point. The boiling point of nitrogen is negative 195.8. Negative 195.8 degrees Celsius. And the boiling point of carbon dioxide is, I typed in carbon. Guess what the boiling point of carbon is? Take a guess. 48,000 degrees. That's a lot. 4,800 degrees. 4,800 degrees for carbon. Carbon dioxide is negative 78.5. Negative 78.5. So, I'm kind of taking a long time to explain this because these are the toughest types of questions you would ever see on the Regents. How do you separate a homogeneous mixture of gases or liquids? Use their boiling points or freezing points. Why am I writing their boiling points? Because if they're a gas and you cool it down, what happens at these temperatures? If those are the boiling points, but they're already gases. If you cool it down, what happens at the boiling point? To separate gases, you can decrease temp until each one condenses or freezes. So, maybe we're a little confused. Maybe I should explain this a little bit. Let's just talk about water. What's water freeze at? What's the temperature? 0 degrees. So just watch, don't write. 0 degrees Celsius is the freezing point of H2O. What do you think the temperature in this room is? Take a guess. Dang it. Someone put it in Fahrenheit, not keeping it in Celsius. Go ahead, guess.
67.
Close. 68. Guess what that is in Celsius? Any idea at all? 20 degrees. So it's 20 degrees. Oops. 20 degrees is room temp, we'll say. And then what's the boiling point of water? 100. Boiling point of H2O. Okay. Tell me, from 0 to 100, so this whole section right here, room temp is in that section. What phase, what physical state is water in? Raise your hands. Laura, close enough. In this room, what physical state is water in? Liquid. So water is a liquid. Let's say we jack the room up to 120 degrees Celsius. Okay? Good luck. We'd be in trouble. What? Yes, we'd probably die. Let's just say we could withstand that. What would happen to this water in my water bottle? It would boil at what temperature? 100. So once we rose the temperature in this room to 100, that would boil. Okay? Then what physical state would water be in? So this would be a gas. This would be gas. So from here to here, 100 to 120, water's a gas. From 100 to 0, it's a liquid. Let's say we chill the temperature in here, right? We chill it to negative 20 degrees Celsius. So from 0 to 20, what physical state would water be? Solid, right? It would be a solid. From there to there. So at 0, it's going from a liquid to a solid, or a solid to a liquid, depending on which way we're going. At 100, we're going from a liquid to a gas to a liquid. So if water is in an environment above 100, it's always a gas. If water is in an environment below 0, it's always a solid. Anywhere in between them, it's always a liquid. You know this, you just maybe didn't really think about it clearly. So now, apply it to this. If these are all gases in this box, this is the boiling point for all of them. This is the boiling point for all of them. Just like this is the boiling point for water, 100. If all of these are in this box and they're gases, so let's say the box is at 25 degrees Celsius, okay? Let's say in the box it's 25 degrees. So all of these, about room temp, a little higher, a little warmer. All of them are gases. We want to separate them by decreasing the temperature in the box. So what happens when we hit these temperatures? That's like hitting 100 for water. So let's say in this room it's above 100. When we lower the temperature to 100, what's going to happen to the water? It's going to become liquid. Slaves with me. I hope other people are with me. If we have a gas and we lower it to its boiling point, it liquefies. And then if we have a liquid and we lower it to the freezing point, it solidifies. So if we want to separate three gases, all of them are way above their boiling point. Okay? This one is the highest boiling point, negative 78. That's the highest. That's the lowest, negative 195. Right? The lower we go, the bigger the negative, the smaller the temperature, colder the temperature. So what we would do is we would lower the temperature in this box until it hits 78.5, below 0. This would liquefy. Once carbon dioxide liquefies, we'd have a little valve here. CO2 would drain out when we seal it. Then you'd have just O2 and N2. Keep cooling it down. When we hit 183 below, it's negative 183, oxygen would liquefy. Then nitrogen would liquefy after that. It's a tough concept for kids sometimes to understand that how can a boiling point be so cold? It's because they're gases. Okay? So I use water to try and explain it and then relate it to something different. Okay? So if you have a homogeneous mixture of gases, you can't boil it, you can't heat it, you got to do the opposite. You got to decrease it. So I hope that's making some sense to you guys. All right, we got to move on. So we talked about heterogeneous and homogeneous. Let's just think of some examples real quick of each one. And then we'll move on and talk about elements and compounds. Okay. So, actually before we do that, are mixtures put together physically or chemically? Monique? Yes, physically. In other words, when we put copper 2 chloride in water, we're not changing the compositions. They're physically mixed, right? Prove it. Physically separate them. That's what we're doing in the back. We'll check it out at the end. All right, so mixtures are physically put together. Okay, let's get some examples of homogeneous and heterogeneous. Homogeneous on the left, heterogeneous on the right. I spelled that wrong. Heterogeneous. Okay. All right. I'm going to actually throw a couple out there. You tell me. Salt water. Where's it go? Homogeneous. Salt water. Okay? Homogeneous. Who remembers from lab what the little notation in parentheses for a solution? It's not solid, liquid, or gas. AQ. Underneath that, put NaCl. AQ. It's a solution. Write all that. Solutions are homogeneous. What if I put sand in my salt water? Becomes heterogeneous, right? So sand mixed with salt water would be heterogeneous because you can see the sand, you can filter it. All right, let's think of some foods. Let's just get a couple more. Salad. Who said salad? Where's it go? Yeah, salad over here. Good. Throw them out there. What? Soup. What kind?
Tomato.
Good. Which one is that? Yeah, tomato soup would be homogeneous, right? Tomato soup. From besides Michaela. What do you got?
Pizza.
Yeah, pizza's over here. A few more. Then we'll move on. What? Vinegar. Vinegar we eat, drink, or whatever you do with it. Okay. It's kind of a compound. It's a compound. Vinegar, pure vinegar is a compound, but the vinegar that's diluted in the store is a mixture. So which one? Homogeneous, right. Someone give me another heterogeneous. Cookie dough ice cream, that would work. Trail mix, yes, I love me some trail mix. All right, so it seems like you have a decent idea. Okay, your homework's gonna practice more of that. All right, moving on. Hopefully you got that. Okay, oh, and your homework's gonna talk about this word. You don't have to write it. Oops. Yep, that's right. Chromatography. Raise your hand if you're familiar with that, or you talked about it before, or you've done it before in lab. One person, two persons.
We all did it last year.
Yes, you all did it. That's why everyone's hand should go up. I know that. Okay. So I'm not going to explain it because it's on the homework. We'll talk about it tomorrow. But it's another way to separate mixtures. So it's on the homework, and hopefully tomorrow, if I remember, I'll have something set up to show you how it works. If you forget. All right. Here we go. Elements and compounds. I'm going to get chopped off, but that's okay. It was important spending time on the separating the gases. That's important to understand that. So elements and compounds. They're both pure substances. They're both pure substances. Uniform. Param? What is that? Uniform. I don't know what I just did there. Uniform in composition. So both elements and compounds are uniform in composition. That's kind of where it ends when we talk about both of them together. So I'm going to talk about elements first, then compounds. Elements are the simplest form of matter. They're called the building blocks. Building blocks of matter. Literally everything is made out of elements. If you keep breaking it down chemically, you'll get to elements. Yes, there's smaller particles, protons, neutrons, electrons, leptons, muons, gluons, quarks, all types of weird things, little tiny subatomic particles. They don't really count as matter. So that's why we say elements are the simplest form of matter. So again, uniform composition. I'm not going to repeat it. Elements have uniform composition. All atoms of the same element are identical. And that's because they all have the same number of protons. And the protons identifies the element. They all have the same number of protons. So all atoms of the same element are identical. Have identical properties, physical and chemical. So if each one of you was holding an atom of sodium, and I was holding an atom of sodium, it would look the same and it would react the same. Why? Because it's identical. They're all sodium. They all have the same atomic number, the same number of protons. So we'll start here. This is a Regents question they love to ask. Probably this year you'll see it. First, like 10 to 15 multiple choice. Elements cannot be broken down. Kids want to argue with me. Some kids who know about nuclear chem, they're like, wait, you can split an element? into protons, electrons, energy, nuclear chemistry. Yes. What this means is you can't break it down into anything simpler. We already said that. You can't break an element down into a simpler element. It is as simple as it gets. So elements cannot be broken down. Okay, they cannot be broken down into another form of matter. Yes, nuclear physicists and chemists can take an atom, smash it with a particle, and it basically blows up, and you break it down, and it creates a lot of energy and radiation. Yes, that can happen, but what you're creating is energy and radiation and heat, not another form of matter. So basically, when you try and break down an element, it just disintegrates. So you cannot break it down. Let's stop there. So I want you to come back and